bleomycin iron 3 plus generate superoxide and hydroxyl radicals. So generate for you superoxide and hydroxyl radicals, and when that happens again, as we saw with the others, there is cleavage of the DNA, and of course that stops the synthesis of the replication of the DNA. So we have superoxide and hydroxyl radical production. So very similar, but of course a very complex molecule, but of course mode of action very similar to the others. Then we also have mitomycin C. Again, if you look at mitomycin C, of importance to note is this group there, as found in the anthracyclines, whereby you have the quinone, there, and of course you also have this important group there again, and also this important group there and that important group there, and they're very important in the mechanism of action of the bleomycin C. Again, it's a natural compound and synthesized again by the streptomyces. So that is our mitomycin, and the mitomycin. So if you look at that mitomycin, you find that this is the quinone. So the quinone undergoes reduction. You can see there is a hydroxyquinone. So that's the first step. And the enzyme responsible is NAD. That this N stands for either NADP, NAD or NADP, quinone oxidoreductase. NAD or NADP, quinone oxidoreductase 1, which of course which is used at all NADPH cytochrome P450 reductase. So you can either use NAD or NADP, quinone oxidoreductase 1, or NADP cytochrome P450 reductase, and that is the enzyme that will reduce the quinone into the hydroquinone. This enzyme has been found to be in high concentration within tumor cells. This enzyme is in high concentrations in tumor cells. So when you give this drug, then this drug, most of its activity is within the tumor cells, where it is first of all converted to the mitomycin hydroquinone. You can see that's a hydro, and that's a hydro. That was a quinone, and that's a quinone. Nothing else changes. And then after that, you have loss of a methanol, and that methanol group comes from here. So loss of the methanol group. Once you lose that methanol group, it means now here you must generate a double bond, and that's a double bond which comes there, and you have lost the methanol, and you can see that group there is still there. So you have just formed a double bond here because of loss of that methanol group. And the resultant compound is idlohydroquinone. So as I said, the first step of the mitomycin through the quinone oxidoreductase enzyme, or the cytochrome P450 reductase enzyme, is to generate the mitomycin hydroquinone, loss of methanol, to give us the idlohydroquinone, and this is an intermediate. Now this group now is ready to alkylate the DNA. This group now is ready to alkylate the DNA, and the DNA is able to replace that amide there. It's able to replace that amide there, and it's amino ester rather. That amino ester there, replace that group there, and in placing there, you can see the DNA replaces that group. And indeed, if you look at this, there's alkylation of the DNA. So there's alkylation of the DNA, and then also this group here, and this group here opens up. So this group here, that is the aziridine group. That group there can also open up to give us down an amino group, which is this amino group, and then this methylene group now also alkylates the DNA. So you have that, not methylene, but the group that the electrons that you have there now, so that moves, and therefore this carbon is not satisfied, And because that carbon is not satisfied, it can also bind the DNA. And that is how the mitomycin is able to intercalate or interact with the DNA. So you can see it is can even be able to bind two different DNA strands. That is one, the other, binding them, and therefore they are not free to be able to separate. So mitomycin DNA adduct, all adjoined. Adduct means an addition. So you can see the mitomycin is adjoins the DNA, but it's important to remember that the mitomycin as it is will not be active. It must first of all be activated to give us the iodolo hydroquinone. Again, when the NAD or NADP quino oxidoreductase reduces the mitomycin, you can also have generation of the superoxide radical. And that superoxide radical can again be converted to the hydrogen peroxide, and the hydrogen peroxide will, through the Fe2 plus, will generate, as we had already said, it will generate the hydroxyl. To generate the hydroxyl radical. And of course, this superoxide also is dangerous. So this oxide there, dangerous. And that hydroxyl radicals are very dangerous. So we are therefore saying that we are also saying therefore the NAD and NAD or NADP quinonoxide reductase can interact with oxygen, and the oxygen can be oxidized to the superoxide converted to the hydrogen peroxide, and the hydrogen peroxide can interact with the ion to give us the hydroxyl ions. And as I have said already, the superoxide ions will have an effect on cleaving the DNA, and the hydroxyl radicals will have an effect on cleaving the DNA. So in other words, this drug is having two ways of interfering with DNA synthesis. One, by forming an adduct or by binding the DNA and therefore stopping it from undergoing further replication, or by breaking the DNA through formation of both the superoxide and the hydroxyl radicals, as we had already discussed. That is mitomycin. The other one is streptozotocin. This is an alkylating agent, and so far you're doing that assignment on alkylating agents. It is a nitrosourea. Remember the nitrosourea there. It is a nitrosourea, so it will act like any other nitrosourea in alkylating. It will alkylate the DNA, and once it alkylates the DNA, I'm still waiting for that assignment. Once it alkylates the DNA, then again the DNA will not be able to replicate. So those are the most important antibiotics. So the most important antibiotics. Check whether there is any question. Those are the most important antibiotics. And after the antibiotics, we look at the other category. And the other category from the antibiotics will be the plant products. The other category after the antibiotics will be the plant products, and we start with the vinca alkaloids. Again, the vinca alkaloids have their own mode of action. We can be able to classify them into what you call, of course, they can be mitosis inhibitors. And being mitosis inhibitors, they can do it in two ways. They can either be tubulin inhibitors or topoisomerase 2 inhibitors. They can either be tubulin inhibitors or topoisomerase 2 inhibitors. When they are tubulin inhibitors, they can either block or inhibit the tubulin polymerization or tubulin D or microtubule depolymerization. So they can act in two ways. But what we are saying is that they are inhibiting mitosis. And of course, we know mitosis is when we're looking at the DNA replication. Mitosis was it's part of the M phase. And mitosis is very important for DNA, of course, replication and, of course, synthesis. So we have the first one, tubulin inhibitors. And we are saying the tubulin is a structural protein which is crucial to cell division. You definitely know these things. We did them, I think, early in either first or second year. Tubulin protein acts as a building block of the microtubules, which are polymerized and depolymerized during cell division. Both the processes of the polymerization and depolymerization is important. If you block either polymerization or the depolymerization, then cell division will not occur. Drugs can block this process by either binding to tubulin, and we have seen tubulin is important as a structural protein, and prevent polymerization, or binding to the microtubules. So they can either bind to the microtubules or they can bind to tubulin. Binding to the microtubules to prevent depolymerization. Agents which inhibit tubulin polymerization include the vinca alkaloids, where you have vincristine, vinblastin, videcin, vinorelbine, which are alkaloids derived again from Catharanthus roseus. And again, this is a plant and can bind to tubulin to prevent polymerization. So these ones will bind the vincristine, vinblastin, videcin, vinorelbine, will bind to the tubulin and they will prevent polymerization. We also do have the podophyllitoxin. This is another plant. We're going to look at them. Forms a complex also with tubulin and prevents the synthesis of the microtubule. So that also that drug, we're going to look at it. It is not a vinca alkaloid, so I don't know why I put it there, but it should come later. These drugs are cell cycle specific. The drugs are cell cycle specific, and they will interfere with the M phase. Remember the M phase, we said it has the mitosis and the I think the cytokinases. So it will interfere with those with that M phase, and therefore block the mitosis. And once, of course, you block the mitosis, we are blocking the cell division. So definitely remember that cell must divide. You have to have the replication of the DNA. You see, the DNA will have replicated when everything will have been formed, but the cell must divide. But now the cell cannot divide. So it means you will find the contents have replicated, but it is not dividing. So definitely you cannot form the daughter cells, and therefore the process of growth and development cannot continue. And you can use vinblasting in systemic Hodgkin's disease, and even informers, vincristine with prednisone for remission of acute leukemia. And we have, these are the drugs we are talking about. So we have, you can see again, they have complex structure, mainly looking like it has two portions. It has the catharanthine subunit, which is the top portion, and the vidoline subunit, which is a lower section. So this section here, the whole of this section here, like that is a vidoline. And then, of course, our catharanthine. The catharanthine subunit, again, catharanthine subunit is now this top one there. Catharanthine subunit, that top one there. And all of them will have those two sections. And if you look at, we're going to look at the differences in a minute. This was just to show us, and then to also appreciate the numbering of these drugs, that the numbering is starting from the vidoline subunits with this nitrogen carrying number 1, number 2, number 3, number 4, and so on. And you see some of the changes we'll see, the differences in the different molecules will be in this subsequent there. That subsequent can be different. Also the subsequent at, I think, position 4 can be different. And also the subsequents here can be different. So we'll be able to see the differences in the different molecules. So let us look at that. And we can see we have vinblastin, vincristine, and videcin. And vinblastin, so this is a general structure, and these are R1. So the nitrogen, which we say it carries the position 1. You see whether I have another one which, I was thinking I have another one which, oh, that's another drug. So we have this position here. In vinblastin, it is a methyl. Then here at position 1, 2, So it's position 3. So you can see position 3, X can change. X is a methoxy group in vinblastine. Again, position 4, again, R3 is an acetyl group in vinblastine. So when you look at this group in vinblastine, it is an ester. When you look at this group, you also put in an O-methyl, so it's also an ester. Then that is a methyl. So those are the 3 groups. So this is a methyl group. That is an ester. You add an OCH3, so that's an acetyl. You add an OCH3, that becomes an ester. Here you add R, you add a CO methyl, again that becomes an ester. So that is vinblastine. When you look at vincristine, the difference is in R, whereby this is an aldehyde group. That is an aldehyde group. It was a methyl in vinblastine, and the other groups are the same. So for vinblastine and vincristine, the difference is only on the N subsequent, where in one it's a methyl and in the other one it's an aldehyde. When you look at vidacine, then R1 again is a methyl, like in vinblastine, but this becomes an amide. X is an amino group, and this is a hydrogen. So this becomes a hydroxyl group. So you can see those are for these 3 drugs, the areas that are changing are position 1, X at subsequent at position 2, and the subsequent at position number, no, sorry, not number 2, number 3, and position number 4 to give us vinblastine, vincristine, and vidacine. When we come to vinorelbine, again in vinorelbine, you look at this, it is, I think it's very, very close to the vinblastine, very close to the vinblastine. You can see that's a methyl group, like in vinblastine, and then X, which is in the next position, is a methoxy group here, this methoxy group, and indeed, even the R3 is the same, is an acetyl group. This is R3, which is an acetyl group, just like in vinblastine. That this X again is the same, just as in vinblastine. Then this group is the same. So in the lower section, the vinorelbine and vinblastine are the same. So there must be another structural difference, and that structural difference, you find it in this position up there. Let's confirm which position that is. It is in position 4'. At position 4', you find this position here. You look at that position here, and you look at this position here. There's a removal of the hydroxyl group in vinorelbine. You remove the hydroxyl group of vinblastine. Remove of that hydroxyl group. Remove of the hydroxyl group of vinblastine, and once you remove that group, then you put a double bond. So this, you put a double bond. You can see this is a piperidine ring. Pyridine ring, so it becomes a dihydropyridine ring. So you put a double bond, and that carbon is still satisfied. So the difference between vinorelbine and vinblastine is at position 4', because you look at the numbering. The vidoline subunit and the cathalanthine subunits are numbered separately, and the vidoline subunit carries the normal numbering, whereas the others carries the prime. That becomes prime 4'. So you remove that hydroxyl group, you put a double bond here, and you're left with the ethyl group, and that will give you a vinorelbine. So again, you can see there are very minimal structural differences, very minimal structural differences, and most of the other rings are intact. So you can see again, this is a rigid ring. This a rigid ring, does not allow for matrix flat rigid rings, again to allow for these molecules to interact or to intercalate between the 2 strands. And then of course they have groups, they have the amino groups, they have groups that can be able to interact through the different bonds that we have talked about. This is just to show how the polymerization occurs. So you have that is the metaphase, how it occurs. You have your chromosomes, and then you have the formation of your tubulin, and the tubulin has undergone polymerization. So tubulin molecules start to form, to form the mitotic speedo. There you have, and then when now they undergo the next phase, which is anaphase, from metaphase, then you can see formation of the microtubules, and this, once you form the microtubules, you allow for easy division along that line. So you find that now this become a daughter cell with everything. It has all the chromosomes, and that become another daughter cell. Now, when you have the polymerization, you find tubulin molecules fail. So when you have the drugs that block the polymerization, like what the ones we have talked about, they block the polymerization, then the tubulin molecules fail to polymerize in the presence of Vinca alkalides. They do not polymerize. This is what we are calling the formation of this, is what we are calling the polymerization, forming a big molecule. And polymerization is to form a big molecule. So you can see they're able to form a big molecule, then which separates, it's pulled apart. So this big molecule is pulled apart to form the microtubules. So they do not polymerize, they cannot therefore undergo anaphase, they cannot form the microtubules, and therefore you will not have anaphase. So there will be dissolution of the mitotic speedo, which leads to cell death. So this is the first method in which they are acting, where they inhibit the polymerization, and we discuss the Vinca alkaloids. So that was the first one, drugs that inhibit the polymerization. We have the second lot that will inhibit the depolymerization. Allow me, sorry, to tell them to pick the little gun. So we were looking at those that will influence polymerization, inhibit polymerization, but we also said we have tubulin inhibitors, and they inhibit depolymerization, which is also important if cell division is going to occur. And these ones are different class of drugs. We have like paclitaxel, Taxol, and the semiscendent analog docetaxel are important anticancer agents that will inhibit depolymerization. The binding of paclitaxel accelerates polymerization and stabilizes the resultant microtubules, which means that depolymerization, in other words, it freezes the whole system. After you get the polymerization, it is stable, and therefore it does not allow to formation. You form the microtubules, but they cannot undergo depolymerization because, and you require them to depolymerize. In other words, kind of to form smaller molecules. So you have polymerization, so you get the microtubules, the stretching out, and now preparation for cell division. But as the cell division is happening, they must also form the small molecules so that the cell can cut through. But that does not happen, and they freeze, and therefore do not allow for complete formation or for complete cell division. So the binding of packet accelerates polymerization and stabilizes the resultant microtubules, which means the depolymerization is inhibited. As a result, the cell division cycle is halted. And we can look at that process. And this is what we are saying. Again, this is a normal cell division. Now, when you give a drug like paclitaxel that blocks depolymerization, we are saying you have stabilization of the polymers. So you have stabilization of the polymers. So therefore, anaphase does not happen. They do not allow for formation of anaphase. Unusual stable tubulin molecules stack and fail to depolymerize. So they cannot allow for formation of anaphase. And once again, you don't form anaphase, then again, of course, you will have no cell division. Cell remains frozen in metaphase. Whereas the other one, we found it was not able. When we gave the drugs like the vinca alkaloids, we found that it's not able to form the polymers. So here it forms the polymers, and the polymers remain stable. So they cannot allow for anaphase again to occur. Taxanes hyperstabilize microtubule structure, kind of freeze them. Taxane binds the beta subunits of tubulin, the resulting microtubule. Taxane complex does not have the ability to disassemble. This adversely affects cell function because the shortening and lengthening of microtubules is necessary for their function. They must lengthen, like they are lengthening here, they must lengthen, and then they must shorten. You must depolymerize them. They must lengthen, and then you depolymerize them. In other words, shortening them. And once you shorten them, then definitely, then you will form your cells. But once you freeze them, you make the polymerization very stable, then again, cell division fails to occur. And that can be brought about by either paclitaxel or docetaxel. Docetaxel is the synthetic derivative of paclitaxel. Again, you can see these are complex structures, quite complex structures. And one is, so you can see the major difference here, this group here and this group there are different. This structure here are the same. The main difference is this group that is there between docetaxel and paclitaxel. That's a different group. So you can see here you have a phenyl amide here, and the phenyl amide here is substituted for. We still have the amide group. The amide group is still there. So indeed, it's a phenyl group. That phenyl group is replaced with a tert butyl. So the phenyl group is replaced with a tert butyl to give the docetaxel, which is indeed a synthetic derivative of paclitaxel. That is our paclitaxel. And if you look at the paclitaxel, it has different areas. You can see we are numbering it from position number 1, calling that position 1, position 2, which is the oxane ring, position 3, an acetyl, an oxyacetyl group, and then position 4, an ester linkage, position 5, a hydroxyl group, again position 6, a hydroxyl group, 7, a phenyl ring, 8, a phenoxyl group, acetoxy group, a bonyl group, and a hydroxyl group. And we are saying some of these groups you can change them, others have to remain fixed. So let us mention some of those groups. You're saying the hydroxyl group in position 1 is not essential, can be removed, epimerized, or esterified. So we are starting with position number 1, this group there. That hydroxyl group is really not necessary for activity. This is paclitaxel. That group is not necessary. It can be removed. It can be epimerized. In being epimerized, you can see this is a beta orientation, means it can also carry the alpha orientation, or you can esterify it with no change of activity. So that's position 1. Position 2 is the oxetane ring. Oxetane ring, it's 1, 2, 3, 4, oxetane ring. And we are saying the oxetane ring or a small ring analog is essential for activity. So that ring there, you cannot change it. You have to change it, you have to give a similar ring, but a smaller ring. And therefore, that is necessary for activity. The presence of the acyl substituent at position 3 is an acyl. That's an acyl group there. Acyl substituent at position number. So acyl substituent at position 3, 4, and 8 are necessary for activity. And acyl substituent is an acyl substituent is when you have an R, C, double bond, oxygen. So that's an acyl substituent. So we are saying at position number 3, and if you look at position number 3, we have an acyl substituent there. At position number 4, Again, we have an acyl substituent there. This is our R, C double bond O. So this is our acyl substituent there. A phenoxyl group there, which is an acyl substituent. At position 8, again, we have also phenoxyl substituent there, which is also an acyl substituent. So we are therefore saying the acyl substituent at position 3, at position 4, and at position 8 are necessary for activity. So you can see, so we are left with that there. That one we have not mentioned it. So those are necessary for activity. Other acetoxyl and benzoloxyl groups present in the natural product will be replaced. So the only ones we are saying are important are that one in position 3, position 4, position 8. If you have any other similar substituent, whether acetoxyl or benzyloxy, meaning you have an acyl group and an oxygen, acyl group and an oxygen, all of them, all the others apart from position 3, position 4, position 8, the others you can't remove them. They are not necessary for activity. Removal of the hydroxyl group at position 5 only leads only to a slight decrease in activity. So that hydroxyl group again, therefore it will result in decrease in activity. Therefore, we can't say it's necessary for optimal activity. Then we go to position 6. Again, we have a hydroxyl group, just like the one, this you can see it's alpha, this other one was beta. A free hydroxyl group in the side chain is required. That is at position 6. It is necessary for activity. And therefore, if you are to esterify it, you must esterify it. In case you want to increase the lipid solubility, you must esterify it with esters, or you must make esters that are readily hydrolyzable in the body. So esterification is possible if the ester group is easily hydrolyzable, leading to a variety of water-soluble and cell-specific paclitaxel prodrugs. So that, if you esterify that, then the resultant drug will be a prodrug. You do require a free hydroxyl group for activity. The phenyl group at the end of the side chain or a close analog is required for activity. So this again, that phenyl ring there, or close analog. When we talk about close analog, we have talked about isosteres like the thiophene ring. So phenyl ring, all its isoster necessary for activity. Again, that group must be there for activity. Reduction of the carbonyl group at position number 10 leads to slight improvement in activity. So that carbonyl group can be reduced with slight increase in activity. Again, the changes are so minimal. Changes that are there, so minimal. Changes are minimal. And therefore, we do not really have, apart from the one we have said, that the docetaxel, we do not have many other drugs that have been synthesized and have the same or bring about the same activity. All right. Then from there, you're still on plant products. The other plant products, the epipodophytotoxins, and under epipodophytotoxins, you have the toposide and the teniposide. Those are the two drugs. Again, that is their general structure. And this is the structure of the podophytotoxin. So the podophytotoxin is this molecule, which again, you can see, apart from, of course, this group here, when you have this sigma bond there, this means it can rotate. But although this can rotate, you can see we do have this planar molecule. So you can see that being repeated in almost all these structures. So you can, although because of this can rotate and can have, and that's why we are saying it can have a sigma orientation, can have a beta orientation. Although that can happen, this can change. You still can see the whole of this structure there, across there, the whole of that molecule, which is 1, 2, 3, 4, is a tetracyclic molecule, rigid molecule, which allows for the fixing or the fitting or the intercalating or the intercalating of this molecule between the bases. So that again, you can see there. When you look at the toposide, the difference is very small. When you look at the toposide, this is our R here. So the podophyllatoxin, as I was saying, it is the rigid molecule without at position 4, without a sugar at position 4. But with the drugs, both the toposide and teniposide, you find that the hydroxyl group at position 4 has undergone a glycosidic linkage with a sugar. There's a glycosidic linkage formed here to give us both our toposide and teniposide. And now the difference between the toposide and teniposide is a substituent. Is the substituent within. This second one is actually not a sugar. It has 2 oxygen. This is not really a sugar. So the sugar one is, this is a sugar moiety. So this is not a sugar. So the difference in these molecules is the substituent in this second molecule, whereby you can either have a hydrogen, a methyl group there for a toposide, or you can have a thiophene moiety there for teniposide with retention of activity. Again, the numbering of this tetracycline molecule, again, we are starting with DCBA, just like the tetracyclines and the anthracyclines, and then our benzene ring carries the prime numbers, 1 prime, 2 prime, 3 prime, and so on. So we are starting for this molecule, we are starting numbering, and of course, where the benzene ring joins, and the ring C, 1, 2, 3, 4, then 5, 6. We forget this is a dioxo. 6, 7, 8. In fact, you can see the rigid rings are these two. Even this one is quite rigid, but you can see these 2 rings are the very rigid rings. B and C very rigid. So 1, 2, 3, 4, 5, 6, 7, 8, and then those are the only ones which are numbered. These are dioxo, and this is a furan. So it's a furan. The D is a furan. Is a furanone because of the fact that it has that carbonyl group there. So DCBA, and the rings that are numbered are only C and B, and that's podophyllene. You do a substitution at position number 4, and you will be able to get your drugs. The semi-synthetic glycosidic derivatives of podophyllatoxin, that one we have already seen. So they are semi-synthetic glycosidic derivatives. I believe that we were able to see the drug show selectivity for cancer cells as a result of elevated enzyme levels or enzyme activity in the cancer cells. And we had mentioned this. Sometimes these cancer cells have higher levels of certain enzymes, and that's the only selectivity that you can go for. Where these cancer cells, they have concentrated like that other enzyme we did talk about when we were talking about mitomycin, whereby you have a concentration of the oxidoreductase, and that enzyme, therefore, you can block it. You can be able to block it, and once you do so, then you can be able to get good activity. So drugs show selectivity for cancer cells as a result of elevated enzyme levels or enzyme activity in the cancer cells. Primary mechanism of anti-cancer or anti-neoplastic action is poisoning topoisomerase 2, just like in the anthracycline antibiotics. So again, remember, these enzymes are mainly poisoned by either by free radicals or ions, super ions, like the superoxide ion or the superoxide radical, the hydroxyl radical. Also bind to tubulin and inhibit mitosis. They also bind to tubulin and inhibit mitosis. They stabilize the cleavage ternary drug. See, the ternary is where you have the drug, you have the enzyme, you have the DNA. So you have the drug, the enzyme, the DNA complex, stimulating DNA ligation, but inhibiting resealing. When you talk about this enzyme, is like the topoisomerase 2. So the drug binds the topoisomerase 2, and of course also the topoisomerase also binds the DNA. So that complex, drug, topoisomerase, DNA complex, is highly stable, and it will generate radicals. It will help to generate radicals that will help in ligation or cleavage or breakage of the DNA without allowing for the sealing. Because remember, there is in a normal cell there is also repair, but in this case, when you have given this drug, the repair does not occur. The DNA topoisomerase fragments accumulate in the cell, ultimately resulting in cell death or apoptosis. Cell death or apoptosis. So again, we are saying these drugs are specific for specific enzymes. They bind those enzymes like this one in binding, giving us a very stable complex. That complex gives us what we are calling the poisons, and those poisons will cause cleavage of the DNA. The RNA transcription process is also disrupted by the interaction of the epiphototoxin with the topoisomerase 2 alpha. And therefore, we are saying the DNA damage through strand breakage induced by the formation of a ternary complex of drug DNA. That one we have said. Once this complex is formed, as we had said, it triggers the formation of radicals, triggers the formation of superoxide ions, and in itself, this causes the breakage of the DNA. Block cells, it is also cell cycle specific. It will block the cells in the S and G2 phase of the cell cycle through inhibition of the topoisomerase 2. That, in other words, these are drugs that they do not have just one mode of action. There will be tubulin inhibitors, and of course, they are mitosis inhibitors, and they're mitosis inhibitors by having an influence on the topoisomerase enzyme. They are topoisomerase poisons, and because they are topoisomerase poisons, they will inhibit, they will block, they will cause the breakage, they will form this complex and cause the breakage or cause the inhibition of the topoisomerase enzyme. And once they do that, then of course you will not have mitosis. And the minute you do not have mitosis, then for sure you will have, of course, the cell will not divide and the cell will just die. The other topoisomerase poison is the camptothecins, and under that class we have the camptothecin itself. Again, this is the structure we have here of the camptothecins, and it's the difference is very slight. That when you have camptothecin, all these are hydrogens. For camptothecin, all those are hydrogens, and then you can have topotecan, where R1 is hydrogen, R2 is a dimethyl amino methyl group, dimethyl amino methyl group, and then R3 is a hydroxyl group. That is topotecan. Then you can also have irinotecan. You can also have irinotecan. And when you have irinotecan, you have this slightly complex group there. You can see it's a this is a piperidine. So it's a dipiperidine acyl. No, it's a dipiperidine ester derivative. Dipiperidine ester derivative. And you can see this is now being put at R3. But the resultant drug, irinotecan, is indeed a prodrug. So when you put this very complex piperidine ester derivative, then the resultant drug is actually a prodrug. Does not have activity. It has to be activated in vivo. We have these ones. So it's a naturally again occurring compound. It targets the complex between DNA and topoisomerase 1. Again, the same thing as we have looked at before, that you have the complex between the DNA and the topoisomerase. So these drugs bind. So there is a combination DNA. So there is a drug DNA topoisomerase 1 complex. This leads to DNA cleavage and cell death if DNA synthesis is in process. These agents are also toxic to cancer cells which are not synthesizing new DNA. So they are toxic to both dividing cells and cells that are not dividing. This is due to an alternative mechanism of action, possibly the induction of destructive enzymes such as serine proteases and endonucleases. So they can act both on the cells that are dividing and those ones that are not dividing. So therefore, the camptothecins can be quite highly effective. Therefore, so selectivity for cancer cells over normal cells, when the cancer cells have higher levels of the topoisomerase 1 than the normal cells. So again, selectivity, very, very slim, very thin selectivity, because of course both the cancer cells and the normal cells will have the topoisomerase 1, but you'd expect that in the cancer cells, the topoisomerase enzyme will be in higher concentrations, and therefore these drugs will go for more for the cancer cells than the normal cells, but they will still cause some damages in they still bring problems in the normal cells, because even the normal cells do have the enzymes. Finally, we have now looked at the mitosis, whereby we do have the tubulin synthesis, where you have the polymerization, depolymerization, and you have also the topoisomerase poisons. We have looked at those two classes of drugs. I think the final one is where you can have what you call the protein kinase inhibitors. You find that proteins require to be phosphorylated. For the proteins to be active, they require to be phosphorylated. And for the proteins to be phosphorylated, that phosphorylation is catalyzed by kinases. So not just necessarily tyrosine, by different kinases, depending on the amino acid within the protein that you are phosphorylating. So the kinase, the name of the kinase will depend on the amino acid. So the amino acid within the proteins require to be phosphorylated for them to have to be active, and therefore, once again, you have the protein kinase inhibitors. You will not activate the proteins, and therefore, some of the processes will not go on. And we do have examples of these drugs. We have imatinib, geftinib, eltinib, sorafenib, sunitinib, and lapatinib. You can see again, because of the similarity in their mode of action, their names are also very, very similar. The protein kinases, which you call the PTKs, are enzymes that regulate the biological activity of proteins by phosphorylation of specific amino acids with ATP as a source of the phosphate. Binding induces a conformational change from an inactive to an active form of the protein. So that before the proteins even can be used, even as structural proteins, they require to be phosphorylated, and that will be catalyzed by the kinases. And as I have said, the kinase, the name of the kinase is dependent on the protein. The tyrosine kinases are those that phosphorylate the tyrosine phenolic hydroxyl group. There are three main types of protein kinases, which are classified according to the amino acid cited that they may phosphorylate. We have the tyrosine kinases, those ones will phosphorylate the tyrosine phenolic hydroxyl group. We have the serine threonine kinases. Remember, serine and threonine do have a hydroxyl group. Even when we were looking at the dactynomyces, we did mention the threonine and so on. So the serine threonine kinases that phosphorylate the hydroxyl group of these two amino acids. Then you have the histidine kinases that phosphorylate the nitrogen of histidine residue. So we have mainly those three. You can have others: tyrosine kinases, serine threonine kinases, and histidine kinases are some of the very important kinases that you have. Resistance develops mainly due to point mutation in the kinase enzyme. That usually does happen. This enzyme can keep changing a little bit. The enzyme can either be the active site be blocked, or you can have a mutation. They are metabolized. These drugs are metabolized through cytochrome P450, specifically cytochrome 3A4, formation, oxidation, and the metabolites are excreted in the feces through the bile. Adverse drug reaction, you can get quite a number: abdominal pain, vomiting, fluid retention, pleural effusion, myalgia, and congestive heart failure. So these are some of the toxic effects that you can have. But we have said these drugs, almost all of them have quite some severe toxicity. You also have others like dasatinib and nilotinib. They're also similar drugs used in case of imatinib resistance, because we have said you can have resistance, and in case you have resistance, you can have other drugs. Because if you have total resistance, then you'd have to change the choice of drug. And this is all we are saying, like this is tyrosine, and of course, this is a hydroxyl group that we are looking at, and we're looking at the tyrosine kinase. You have ATP changing to ADP, so you're only losing a phosphate, and you find that your hydroxyl group has been phosphorylated, and that activation of the cell processes. That is just one example. And of course, we have several examples, and these are just examples of the drugs that we have mentioned. Having their structures have no structural resemblance. They are different compounds. And I think that finishes the protein kinase and the mitosis inhibitors. And now we finally, I think this is what now we discuss next time and hopefully finish, is a hormone therapy, because I think time is up. So we have now the hormone therapy and the alkylation, which we should be able now perhaps in another 2 lessons to finish, so that we finish the anti-cancers and move on to the antiviral drugs. At least this topic has only those two. The others are very many small topics, but this one has only those two. So from the next lesson, we will now be able to, we'll go to the hormones. So please again, look at the structures of the hormones. That they classify the hormones that are used in the management of cancer. They're quite, you can classify them. They are the estrogens, the agonists, the antagonists, the progestins, the androgen derivatives. There are quite a number of them. And understand why would you use the hormones to be able, why would you use hormones in management of cancer? With what kind of cancers do we use them? Of course, we can use them as either antagonists or as either agonists. Because do remember again, if you give an agonist, like if you give an agonist, especially if you can give an agonist to the men, give an agonist, you will block the production of testosterone. And once you block the production of testosterone, then you can be able to have some control of prostate cancer. So please draw those, classify those different drugs, the aromatase inhibitors, the progestins, the glucocorticoids, all of them, classify them, draw examples. You have drugs like tamoxifen, ethinyl estradiol, and so on. Draw those drugs, the structures of those drugs, so that now next time we should be able to finish on hormone therapy and perhaps even start now on the alkylating agents and summarize on the anti-cancer drugs. Any question? So when am I getting the assignment? When am I getting the assignments? And kindly sign in with class rep. Class rep. Frida. Frida, are you there? Frida. Deputy class rep, are you there? Frida, are you there? Oh, can you sign in for present? Frida, are you there? Or even if you can't talk to me, organize to take the assignments and put them in my pigeonhole. I can pick them anytime. I think now it's past 2 weeks and I need to start marking. So organize that I get the assignments. I can pick them anytime. And then I need to give you an assignment for antivirus. I think I'll do that in this coming week. Did I give you the assignment on anti-cancers? I don't know. Yes, and calculating agents. So and I think that will serve for that assignment. Can't have too many. And we did have a simple one on the narcotics on the tramadol. To make sure the structures, most of the structures for the, especially the plant product drugs, are quite complex. So nobody would expect you to know them, but you need to know the areas that can be structurally modified. And of course, you need to know some of those compounds, the chromophore, the structural requirements for those molecules for them to have the activity that they have. And in each of the groups, I have stressed the structural requirements that are really necessary. Now I have 40. Where have you come from? Where you are 40? Were you there throughout? Surely. Remember, you come to class for your own sake, not for me. And it's not for me, it's for your own sake. So don't lie. When you come to answer the questions, we will know whether you come or don't. So we were to also organize to start having the fast cards. Frida, I don't know whether you are there or you are not able to talk to me, or Frida is present. So please organize with the students. When can we have our fast cards so that the cards are not too broad? Even as you organize, that I get the assignments and we start marking. So I hope everybody has signed in. Thank you for your presence. And we meet next week. We meet, I think, on Tuesday to discuss the narcotic analgesics.